Hello everyone, I'm Lara and I'll be there as a tech support during the tutorial. I want to introduce you to our tutor, Milica Maricic. She's an assistant professor at Faculty of Organizational Sciences, University of Belgrade, and she will hold the Lasso and Ridge regression models in R introduction tutorial. Enjoy!
So good morning, everyone. Just for the start, I'm going to turn on the camera just to say good morning, and hello to all of you, and welcome to this tutorial. As I've been introduced, my name is Milica Maricic. I'm an assistant professor at the University of Belgrade, Faculty of Organizational Sciences. I'm a member of the Department of Operational Research and Statistics, and my specialization relies in the field of statistics. So at first, I'm going to share the presentation. At the beginning, we're going to go through some, let's say, theoretical aspects of the Lasso and Ridge regression, and afterwards we're going to see how can we conduct these analyses in R. So for now, I won't be needing the video, so I'm going to share the presentation so we can slowly start. I hope that you can see the presentation. So the agenda of our talk today is the following. So at first, we're going to talk a little bit about the introduction to our topic. Then we're going to talk about linear regression. So in order to better understand both ridge and lasso regression, we need to talk a little bit about linear regression, maybe to go through, to recap some theoretical aspects needed. Also, at the end, we're going to talk about the elastic net model, which is in fact a combination between ridge and lasso regression. So a little bit still more about me, just so you get the idea. So some of my fields of interest are related to multivariate analysis, structural equation modeling, econometric methods, and models of statistical learning. So lasso and ridge regression, which we will be talking about today, can be put within models of statistical learning, also within econometric methods. So at the beginning, the question that we have is how can we, for example, model the relationship between advertising costs and sales? So first, we are maybe interested to see whether there is some kind of a relationship between these two variables. We can be interested in the direction of that dependence. We can be interested in the strength of that direction. But what is also quite interesting and important for us is to see, can we create a statistical model between the two variables and later use that model for predictions. So if the advertising costs are $10,000, what will the sales be? So our idea usually is when we have two variables, okay, we can explore their relationship and their correlation dependence, which is okay, it's good. We get some information from that. But if we want to go a little bit further and try to predict and look a little bit into the future, we need to create a mathematical model. So these are just some of the questions we might have. So in such a situation, we can use linear regression analysis to create a model and later to use that model for prediction. So linear regression models analysis are used for modeling the dependence between 2, 3, or more variables, and with the goal at the end to use that model for prediction. So our goal is to create a mathematical model and later to insert new values of interest in the model and to predict values. So a little bit about the theory. So in regression, we always have one variable which is considered independent, a predictor, and the other one which is our dependent one, or the outcome. So we always have one dependent variable. So we have one variable of interest which we want to model. When it comes to independent variables, we can have one or many. It's up to us, up to the complexity of the model, the data we have available, and so on. But it's important to remember and to know that we always have one dependent variable, one which we want to model, and we can have one or more independent variables. We use independent variables to explain and to better understand our dependent variable. So also in the lines below, we have some assumptions of the linear regression. So the first assumption is that the relationship between our dependent and independent, or more independent variables that we have is linear. So sometimes it is pretty nice to, before conducting a linear regression, that we explore the dependence, just to see whether the relationship is linear or the relationship is curvilinear. If the relationship is linear, it's okay. We can continue and see if we can apply linear regression. If we see that the relationship is not linear, it's curvilinear, then we turn to other regression and modeling approaches. The second assumption is that our dependent variable is distributed normally at each value of our x. So when we are talking about linear regression, we are usually focusing on stochastic relationship which can occur between two variables. Stochastic relationship is such a relationship that for one value of our dependent variable, we can have a list for one value of our independent variable, we can have many values that our dependent variable can take. So this assumption actually tells us and assumes that our dependent variable is going to take all those values by normal distribution. The second assumption is that the variance of our dependent one for every value of our independent one is the same. So you might have heard this before. So this is called homogeneity of variances, or homoscedasticity. In easiest words to explain what homoscedasticity means is that the distribution, so how the distribution of each and every epsilon for each and every x looks like, is the same. So those normal distributions are the same. So the variances of those distributions are constant. And the last one is that the observations are independent. So there is no dependence between different observations which we have measured. So these are just, let's say, basic assumptions of linear regression, which are, usually sometimes tested before conducting a model. So here we have a formula of a simple linear regression model. So our epsilon I is our dependent variable. So that is the variable which we are interested in modeling and learning more about. Beta 0 is the constant in our model. So beta 0, in fact, tells us what is going to be the value of our dependent one if our independent variable takes the value of 0. Xi is our independent variable, so the variable which we are using to model our dependent one. Beta 1 is an important coefficient, which is called the slope. So beta 1 is pretty important because it, in fact, tells us many things about the relationship between the dependent and independent variable. So if beta 1 is greater than 0, then the relationship between the dependent and the independent one is direct or positive. If x increases, y is going to increase as well. If beta 1 is less than 0, if x1 increases, yi is going to decrease. So basically, based on the value of beta 1, the coefficient which stands next to x1, we know the direction and the type of relationship between the two variables. What we also have in the model is the stochastic part. So this part here, epsilon I, is the one responsible for the situations that we, for one value of our independent one, we can have a whole list of values of our dependent one. So this part here, epsilon I, is the one responsible for the stochastic part of the model. So we also have some assumptions regarding our stochastic part. So our basic two assumptions is that we assume that its value equals to 0. That would be the best for us. And the other thing that we assume is that the variance of the epsilon I is constant and equals to the variance of the whole regression model. So this part here, in fact, is related to the assumption which we already mentioned in a way, the assumption made regarding the homoscedasticity of the model. So these are some of our assumptions related to epsilon I. Also, another assumption which we have is that all these stochastic parts for each and every value that we measured on our sample are independent. So there is no relationship between these stochastic parts in our sample. So, do you maybe have some questions for now? Okay. So, the formula that we talked about and which we saw is the model, is our linear regression model on the population. So, basically, in statistics, we usually don't know the true values on our population. So, just to make let's say a small, not an introduction, but to distinct between the population and the sample. So the population is related to each and every, let's say, potential participant which we can have in our research. So, for example, a population can be population of students population of the University of Belgrade. So those would be each and every student at the University of Belgrade. So in practice, it's pretty difficult to, go and survey each and every student of the population. So in order to gain some data with which we can work, so we are going to draw a sample. So basically, a sample is a part of population which we have covered, which we have have measured particular values on. So in practice, we usually don't know the parameters on our population, which is a bit problematic. So what are we going to do? From our population, we're going to draw a sample, and based on the values on our sample, we are going to estimate the true parameters on the population, which we do not know. So this is basically what we do in many statistical tests and statistical approaches. So on our population, the model is epsilon I equals beta 0, our constant, plus beta 1 xi plus epsilon I. So this is the model on our population, and we do not know values of beta 0 and beta 1. So we need to estimate them. We want to learn more about them. From our population, we take a sample, and on our sample, we conduct analysis, and we come up with the estimated model, or the model on our sample. So in practice, we don't know beta 0, we don't know beta 1. Based on our data, the data which we have collected, we are going to estimate our beta 0 with B0, beta 1 with beta 1. So when we are observing our model on the sample, we need here to have in mind and to place our attention to see that here it's not epsilon I, it's epsilon I hat. So every time we have a hat, it indicates that we are observing an estimate. So epsilon I hat, in fact, is an estimated value of our dependent variable by our model. If we continue observing our model on the sample, we can see that now on the model on the sample, we don't have this stochastic part. So in the model on the sample, we do not have the stochastic part. So in fact, what we here made is a, let's say, a deterministic model. So in fact, the formula of our model on the sample in the case of simple linear regression is going to be a line. So the next question which occurs is, how do we find these two unknown parameters? So how do we come up with beta 0, with B0 and B1? So to estimate the unknown parameters within the linear regression model, we will be using the least square method. Okay. So I think that the easiest way to explain how the least square methods work is to observe a graph. So let's say that we have oh, it's not a good photo. Okay, so so what is basically the idea of the least square method? So the idea of the least square method is to minimize the difference between what we have measured on our sample, which is epsilon I, and what we have estimated on our model. So the idea is to try and find a line which is going to go through our data so that the difference between what we have measured on our sample and what we have measured on our model is the least possible. So if we, let's go maybe back to the photo before not working. Okay, so for example, each of these dots is a combination of the data which we have measured on our sample. So this pink dot here, for example, is a dot point with coordinates x and y. So those are the the data from our sample. What do we want to do? We want to draw a line between all these pink dots so that the difference the difference between the dots and the line is the least as possible. So what we want to draw a line so that all these dots are as close as possible to our blue line. So our blue line is in fact our estimated model. So our blue line is the line which we can calculate as B0 plus B1 xi. So as we can see, the difference between what we have measured and what our sample, what our model provides as a value can be positive, as here, or it can be negative on the other side of the line. So if we put value of x in our model, we are going to have this point here, the point on our line. So our idea is to draw a line so that these differences between the dots and the line are the smallest possible. So as those differences can be positive, as here, and can be negative, as here, so to eliminate the possibility of having positive and negative differences, what we do, we are going to observe the square differences. So this is a common approach in statistics. So when we are observing differences, it is quite good for us to observe the square differences, because, as we said, the differences can be both positive and negative. So we are observing the differences between what we have measured on our sample and what our model suggests. We need to observe the square difference, as we mentioned before, and again, we need to sum up all those differences for each and every data point in our sample. So basically, that is the function which we want to minimize. So we want this sum to be as minimal as possible. So how do we find our estimates? So we find them by equaling the partial derivative of this function with 0. So we need to do this for each parameter which we are estimating. So here in this part, you can see the final formulas. How do we actually calculate B0 and B1? I mean, you don't need to learn these formulas. Software does it all for us, but it's good for you maybe just to have an idea what is actually happening in behind, and what is in fact the software using, and how does it work. If we look at the formulas, we can see that those are pretty simple statistics and simple things that you can quite easily calculate based on the data which we have gathered. So using the least squares method, we find our estimates B0 and B1. Okay, so before we slowly continue, do you maybe have any question related to this part? Okay. Good. So as we saw, linear regression models are quite practical. They are understandable, so you can easily communicate the results of your linear regression model even to somebody who is not specialized in, you know, statistics, data analysis, and similarly. So they're relatively easy to implement, as you saw. I mean, those formulas can easily be calculated even by hand. So, and in fact, they are quite simple. So the question which next arises, so if we create a model and that model is statistically significant, can we always use that model for prediction and estimation? The question here which arises is, does it always work? Are we always confident that the model which we have created is really a good and reliable one? Unfortunately, no. Unfortunately, sometimes the linear regression model which you created might not work so well. So that situation occurs sometimes when your model is overfitted to the data which you have collected. So if your model is overfitted to the data which you have collected, it cannot handle new instances good. So, for example, you have some data, you create a model on your data, and you're inserting new data in your model, but that data highly differs from the most of the data you have collected. So in that cases, your model can go wild and cannot handle new instances in a good way. So on this slide, we have, let's say, a couple of graphs so that we can make just a difference and maybe to better understand the concept of underfitting, appropriate fitting, and overfitting. So the first model here that we have in the left part of the slide is the situation when we have underfitting. So we have some data. We want to draw a line between as we can see different types of data so that we can separate them and let's maybe cluster them in a good way. So if we can see here that just simply drawing a line between the two is not a good fit. So our signs are completely mixed on both sides of the line. So in fact, the line is not doing the work for which she was drawn. And in the middle graph, we have appropriate fitting. So now we can see that, okay, there is a line. The line pretty good makes a differentiates between the two types of symbols that we have. It's not perfect. We can see that here in this yellow, let's say, segment, there are two green symbols. But again, we can say that this fitting is appropriate. On the last graph, we have overfitting. So in this case, our line is too perfect. So our line perfectly makes a distinction between the green and the yellow signs. So here our line is overfitted, it is perfect. So maybe if we insert new entities in our graph, our line is going to underperform, which might not be the case here if we have appropriate fitting. So overfitting in fact is not such a good thing to for your model. So sometimes it's better to have appropriate fitting, which is not that perfect, but it is going to deal pretty well with new values which you are inserting in your analysis. So a problem which regular linear regression has is that the model can be overfitting. Okay, so here are some things or occurrences which can lead to overfitting. So the first one is outliers. So I'm pretty sure you encountered outliers before. So outliers are specific values in our sample which are extremely large or extremely small compared to all other values in our sample. So our outliers can be univariate if we are observing variable by variable. Usually we can observe and detect univariate outliers by using box plot. If we are creating, let's say, a multiple linear regression model, so we have multiple variables that we are observing and taking into account, maybe it is better to use multivariate outlier detection methods, such as Malachanobis distance. So outliers can be pretty problematic for, I mean, every statistical method or algorithm which you are planning to conduct. So a good recommendation is to maybe always, prior to conducting an analysis, that you observe whether there are outliers or no. This can help you quite a lot. I mean, not to lose a lot of time trying to model something which is completely which is distorted by outliers. Sometimes it is definitely better to delete an entity or two than to try to model highly distorted data. Okay, so the next issue which can lead to overfitting is the situation when we have a small sample and a large number of predictors. So this can actually happen usually in, let's say, medical research. When you have small samples, small number of patients within a survey, and you have a large number of predictors which you are dealing with. So some statistical literature tells and suggests that for each and every predictor, you need to have at least 10 entities. So, but I mean, the larger sample you have, the better you can create a better model. The next one is that your training data is not adequate. So maybe when you were creating your training data, it just didn't work well. The other, also a thing which can lead to overfitting is that predictors, you have predictors which are not correlated with the dependent variable. So this is also a thing that we can maybe talk a little bit about. So when you are creating a multiple linear regression model, so in that model, you will be having 2, 3, 4, many independent variables in your model. So also a problem which can occur is that when your independent variables are highly correlated among each other. That specific situation, when your independent variables are highly correlated, is called multicollinearity. So multicollinearity can be a really big problem for any type of linear regression. So if you have multicollinearity in your model, the least square method is not going to work well. You're going to get estimates which are not statistically significant, estimates with high standard deviation, and so on. So multicollinearity is in practice quite often detected. So the best solution if you have a problem with multicollinearity in your model is to just remove one of the variables or those variables which are highly correlated among each other. So multicollinearity, dealing with multicollinearity can be very helpful in sense that you can simplify your model. That is pretty good, especially when you have large models with a lot of independent variables. So also going back to the sentence saying that predictors which are not correlated with the dependent variable. So also it is good to maybe explore and to see whether your independent variables have some kind of connection with your dependent variable. I mean, it's inserting variables which are completely not correlated can be problematic, and in fact makes no sense. Why would you insist in putting in your model a variable which is not at all correlated with your dependent variable? But at the same time, why would you insist on putting a predictor which is completely or highly correlated with your dependent variable? So in that sense, when you are choosing the variables which will be in your model, you should take into account the relationship between individual predictors and your dependent variable. So in order to deal with the issue of overfitting, the solution which comes up is regularization. So what does in fact regularization mean to us? So idea of regularization is to reduce overfitting, to increase our model reliability, and to improve our prediction and estimation accuracy. So in linear regression, especially when we have large models, model complexity can lead to later a really complex model which is complex to interpret, to estimate, and so on. But at the same time, if we create just a simple model, like a simple linear regression model, that we can create a biased model. So the idea of this regularization in fact is to help us find some kind of a balance, not to have a too complex model, but not to have a too simple model. So the idea is to find a measure somewhere in between to create a model where we have a balance between our biasness and the variance. So the idea of regularization, what are we trying to regulate with regularization, is to create restrictions on our regression coefficients. So we want to have some restrictions on the values of our estimates. So basically, regularization is going to reduce the value of our regression coefficients. Okay. So the idea of regularization, maybe what can we have in mind, is the simplest, the best. So we want to find a more simple model. So when it comes to regularization within linear regression, we have two basic model constraints, which we are going to add to our least squares. So we have L1 penalty. So L1 penalty states that the sum of the absolute values of the regression parameter estimates should be smaller than some constant. The other penalty which we have is that the sum of the squares of the regression parameter scores should be smaller than some constant. We're going to go through each and every penalty in more detail, and we can also present them graphically. So as we said, L1 penalty is takes into account and observes the absolute values while the L2 penalty observes the squared values. So basically, the idea for us is here to move this red line until the red line comes and touches the area of our penalty, whether it is the squared penalty or whether it is the absolute penalty or the squared penalty. So we have basically two types of penalties which we can add to our linear regression model, and based on the type of penalty which we are introducing, we have two types of regressions. So the first type of regression and the penalty which we will be using is the ridge regression. Ridge regression uses a L2 penalty. So the first formula here is the formula for the ordinary least squares. So the one which we talked about and which we explained. So we are observing the difference between what we measured on our sample and what our model proposes. So this is what we showed before. So this is the basic ordinary least squares. As we said, regularization, we are just adding additional constraints to our ordinary least squares. So what we are adding here is this part. So as we said, L2 penalty is related to the sum of the squared values of our coefficients. So this is the sum of beta yacht square. So b yacht square are in fact our squared values of our regression coefficients. Parameter lambda is the parameter of ridge regression. We are going to talk a little bit more about the lambda parameter as we continue with ridge regression. So basically, the idea of regularization is to add additional constraints to our initial ordinary least squares. So ridge regression takes into account L2 penalty. L2 penalty is related to the sum of the squared values of our regression coefficients. Okay. Okay, so before we continue, how does this look like for now? Do you maybe have any questions? Okay. So a little bit more then about the parameter lambda. So parameter lambda is a value which must be greater or equal to 0. So also what is, let's say, a little bit tricky is that we need to define this parameter lambda before we conduct our ridge regression. So we need to define the value of our parameter lambda. So if we put value of our parameter lambda, if we make our lambda 0, our ridge regression is going to be the same as linear regression. Okay, if our lambda is 0, this is just a regular linear regression. If our lambda tends to infinity, so as we increase our lambda, all our regression coefficients are going to become close or equal to 0. So it is tricky to find a good value of our lambda. So if we increase our lambda, all our coefficients are going to become 0. So now the question arises: how are we going to find that true and good value of lambda, which is going to decrease the values of our regression coefficients, but not for all of them. Maybe just for a couple of them are going to become 0, a couple of them are going to be reduced. So here is in fact, here is an example how is ridge regression working. So for example, let's take an example where we have a model with 2 independent variables. So we have some beta 1 and we have beta 2, okay, so which we have to estimate. This point here, B, is in fact like a point with coordinates of our estimates beta 1 and beta 2 if we are using our OLS. So this point here, B, is the point with coordinates of estimates which we received after using the ordinary least squares. So what do we want to do? We want to somehow reduce the values of our estimates. So we don't want them to be here and here. We want to reduce the values of our estimates. So our lines are going in circles, and we want to find this value here. So we want to find a combination of estimates for our 2 independent variables, which touches the constraint, the surface of our constraint. So this point here, where the red line touches our blue surface, that is our new ridge regression coefficients. So as we can see, our values of both regression coefficients decreased. So from here, OLS regression coefficients, we want to reduce those coefficients, and this value here, this combination of the two coefficients is by ridge regression the best solution. So as we can see, the values of our estimates have reduced. Okay, so this is also a really good graph, which can maybe explain better how our estimates are changing. So as we said, if our lambda equals to 0, then our model is no different than the ordinary least squares. But what we said, if our lambda increases, the values of our estimates are going to decrease. If lambda tends to infinity, all our estimates are going to be 0 or close to 0. So the question arises, where do we stop and what is the true value of our lambda? So in order to find a good value for our lambda, we are going to observe the following things. So we are observing the biasness of our estimate. We are observing the variance, the estimation variance, and mean square error. As what we can see, as our lambda increases, the bias of our estimate also starts to increase. Also, the estimation of our variance decreases. So what we want to find that, let's say, bliss point where we have a low variance and we have a pretty, let's say, low biasness. So in fact, in this point where the two encounter is the point where our mean square error is the lowest. So in fact, we want to find and we want to use that lambda, which leads to the smaller mean square error, which leads to a good combination of variance and bias. That's what we also mentioned before. So we don't know what is the value of our lambda. If lambda is 0, we're observing regular linear regression. So we want to find a good value of our lambda, which is going to find a balance between variance and bias, and at the same time, which is going to lead to a small mean square error. So basically, that is going to be our way of finding a good value of our parameter lambda. Okay. Okay, so when it comes to both ridge and lasso regression, so they can be done and conducted in the newest version of the SPSS, but of course they can be also done in R and Python. So for this let's say tutorial, the plan is to showcase how do we conduct this analysis in R. So our plan is, so first, before we do and create a ridge regression model, we will create a regular linear regression model so that we can later compare the two. You can't hear me. I'm not sure why is that. Okay. Can you hear me now? Okay, thank you. Okay, so the idea is then, so the idea is to first create a regular linear model to see the values of our estimates, and then to go and conduct a ridge regression model, and then to compare and to see how have the values of our indicators of our regression coefficients changed. So to do so, we will observe the WEF dataset, which I think you have it available. So maybe before we go to, let's say, the practical part, I suggest that we make, let's say, a short break until 10 o'clock. So just that we all have a small break. So in, let's say, 8 minutes, we will continue and see how to do ridge regression in R. So before we, let's say, go to a short mini break, do you maybe have any questions for now? Okay. If you don't have any questions, let's take a short break. Thank you. Okay. Okay, after a short break, we can slowly continue. So as we said, we will be using R as our software, and we will be using the VEF dataset which you were provided. Okay. Okay, so this is our task. So for the first task, we have to create and test a linear regression model of the influence of variables market size score and goods market efficiency on the variable macroeconomic environment score. And we have three additional requests besides just creating a linear regression model. So our first subtask is to evaluate the parameters of our linear regression model. We have to examine the quality of the representativeness of our regression line. So we need to see how good our regression line represents the data that we have collected. And we will use significant tests to explore the individual influence of our explanatory variables using the t-test and to see the significance of the entire regression model using the f-test. Also, there is a question for us to see, is our constant in the model statistically significant or not? So in this case, we are observing, let's say, a linear regression model, which takes into account one dependent one. So macroeconomic environment score is the variable which we want to model. And we are going to model it using market size score. So that can be our X1 and goods market efficiency score, which is going to be our X2. So here, in fact, we have a multiple linear regression model. So multiple linear regression model is a model in which we have one dependent variable and we have more independent variables within it. Again, we will be using ordinary least squares, but just now formulas are definitely going to be more complex. We're not going to dive into the formulas itself. So if what we will be needing to do this, let's say first part, and to do to create our linear regression model, we will be needing to somebody asked, is it possible to get the data set? So I'm just not sure how can I send the data set to the participants. So I think that they shared the data. So you can download the data from chat. So in chat you can find both the presentation and the data set. Okay. So the first two packages that we need to install, first is the package foreign. We will be using the package foreign to import the data set, which is in fact an SPSS file. And the second package we will be needing is the one for, let's say later, maybe graphs and visualization. So first we need to install the packages using the function install.packages. And next, we have to activate our packages using the function library. So the next step then is to import the specific. So Dragana says that chat is disabled for her. I don't know how can we solve this issue. I'm not sure. How can we then solve this. I mean, even if you don't, chat is disabled, sharing it here. How can I then share the data, the data set?
I'll try to share it one more time. Just a second.
Mm-hmm. I mean, if that is not working, maybe you can send me your emails and I can email it to you. If we don't find an easier solution. Mm. Okay, I'm just going to stop share so I can send you the data. Mm-hmm. Okay, does anybody else also has a problem with downloading the data set? You can just send me your email and I'm going to send you the data set via email. It's not a problem. Mm-hmm. Yes. Mm-hmm. Okay, somebody has his arm up. Rock, do you have a question?
No, sorry.
Okay, it's okay. No, it's okay. 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 Okay, I saw. Never mind. I also already sent you the data on your email. But I'm glad that everything is sorted now. Okay, so as we said, we will be for now needing the two packages. First is foreign, which we will be using to open our SPSS file. The second one is related to a package we will be using for visualization. So the data set I sent you is called WEF. So I'm not sure how familiar are you in working in R, but so I might be maybe explaining all the functions, maybe step by step, and maybe in a lot of details, but just to be sure that everyone follows. So WEF is going to be the name of our data set, our object, which we will create within R. The next point is the assignment sign. The function which we will be using is read.spss. So the function will allow us to read an SPSS file. So within brackets, the first parameter we need to insert is the path to where our data is located and saved. So this is the part which is going to differ for each and every one of you. So is it going to be, I don't know, CD, is it going to be downloads, is it going to be your desktop, and so on. So this part is going to differ for each and every review. So maybe the easiest way is to maybe go to properties and just to see the right path to where your data is saved. The other parameter we're going to use data.frame equals true, as parts of our SPSS file have been formatted. So after importing the specific file, what is usually a good thing to do is maybe to get to know your data and explore and see what types of data you are dealing with. So in this case, it's good to use the str function. Str function is in fact providing you the structure of your data. So the results of the str function, it's just going to write you down what are your indicators in your data set, what type of data are you dealing with. After we have inserted our data and we got to know our data, which is mostly continuous variables, as we can see, the next phase is to create our linear regression model. So the function for creating the linear regression model is pre-installed in R. So there is no need to install a particular package which will allow us to create a linear regression model. So again, we need to give a name to our object which we are creating. My suggestion is that it can be reg model 1, like regression model 1. We have the assignment sign. The function for creating a linear regression model is LM, like linear model. So the first parameter within our brackets is how our model looks like. So here it is really important to just remember the order by which you enter your variables and tell R how does your model look like. So the first variable which we are entering is our dependent one. So macroeconomic environment score. So that is the variable which we want to model. The next sign, the tilde sign, in fact indicates and tells R that we are modeling this variable by some other variables. So after the tilde sign, we are entering all our other independent variables which we are using. Also have in mind that between our independent variables, we need to put a sign plus. So it doesn't matter. Later when we have our estimates, it can easily be minus. But to tell R what are all the independent variables which we are using the sign plus. So we are modeling macroeconomic environment score by market size score and goods market efficiency score. Also, we have to tell R which data to use. So here we're going to use the whole data set, the whole sample. So data equals WEF. Okay. So with this function, we're just creating our model. And now we want to see the summary of our model. So we want to see the results and to see whether our model is or is not statistically significant, what are our estimates, and so on. So basically, the first function just creates the model, while the other one evaluates the model and provides us with the results. So this is the output you should have obtained. So The output is pretty detailed, so we can maybe go line by line just to explain what is provided to us. So the first couple of lines are just telling us what is the model which we created. The second couple of lines are related to residuals. Residuals are differences between what we have measured on our sample and what our model estimated. So residuals are those differences, and in this upper table we are just given, let's say, descriptive statistics of our residuals. So for example, the maximum difference between what we measured and what our model provided us is 2.5. The median residual is minus 0.016. So from here we can see that here our residuals are not that much. The table below is more interesting for us. So within the table coefficients, we are provided with estimates of our coefficients. So from table coefficients, we are going to read out our B0, our constant, B1, coefficient which stands next to market size score, and B2, which stands next to goods market efficiency score. So as we can see, our rows are our model elements. Intercept, or our constant, are two independent variables. The first column which we have is estimate. Estimate is the value which is estimated on our sample. So these are the estimates by ordinary least squares. So in our case, our constant is 1.60. The coefficient which stands next to market size score is 0.134, indicating that if market size score improves by 1, macroeconomic environment score will improve for 0.134. In the same manner, we can interpret the other coefficient. So if our goods market efficiency score improves for 1, the value of macroeconomic environment score is going to improve by 0.6. Okay? Next. Anytime that we have a sample and we have our collected data, we can always apply ordinary squares, and we can always get these estimates. But what is quite important for us to see whether these elements, whether these coefficients are statistically significant or not. So we need to statistically test the importance and the statistical significance of these coefficients. For that, we are going to use the last two columns, t-value, which is the value of our statistics, and this PR, which is in fact our significance level. So I'm not sure how acquainted you are with hypothesis testing, but when we are testing hypotheses, we always have two hypotheses: our null hypothesis, the hypothesis which we are in fact exploring, and the alternative one, which we will accept if we reject our null hypothesis. So long story short, the easiest way to make a decision whether we accept or reject our null hypothesis is to observe the significance. So if the significance is lower than 0.05, then we can reject our null hypothesis and accept our alternative one. So if we observe our significances here, we can see that all of them are less than 0.05. So by the values of our significance, we have stars or codes. Here below, you can see what significance of the code means. So the more stars we have, the lower our significance is. So as our significance is always lower than 0.05, we are going to reject our null hypothesis, which states that this coefficient is not statistically significant. So in all three cases, we are going to reject our null hypothesis, and we are going to say that all these coefficients are statistically significant. So this t-test was used to inspect the individual significance of these indicators. The next test which we can observe is the F statistics. So F statistics is like an omnibus test. It tests the overall model. So t-test looks at the individual impacts and individual significance, while the F-test looks at the overall model. The null hypothesis of F-test is that the model is not statistically significant, while the alternative states that the model is statistically significant. Again, if we observe our p-value, we can see that our p-value is pretty low, close to 0, which indicates that we can accept our alternative hypothesis, and we can say that our overall model is statistically significant. Okay. Also, another thing which we can interpret from the output is the quality of our model. So when we are using multiple linear regression, we focus on communicating the adjusted R-squared. The adjusted R-squared is a measure which tells us how good our independent variables, so here market size score and goods market efficiency score, explain the variability of our dependent one. So adjusted R-square takes values between 0 and 1. The closer it is to 1, the better our model is. For example, here, our R-square is 0.182. This indicates that 18.2% of variability of macroeconomic environment score is explained by market size score and good market efficiency score. So this value, in fact, tells us how good our independent variables explain our dependent variable. Looking at this value, we can say that this model is not a model of not such a good model. I mean, 0.18 is not that much. Okay, how does this look like? I'm not sure how acquainted you are to linear regression interpretation and interpretation of results from R. So maybe I took a little bit more time, but just to be sure that everything is clear. Do you maybe have any questions so far? Okay. Okay, after we have created our linear regression model, now we are going to create our ridge regression model. So to create the ridge regression model, we need a new package. So ridge regression is not by default installed in R. So we need to install package glmnet. So we need to install that package, and we have to call it or activate it. Okay. Okay. So glmnet is the package we will be using for both Ridge and Lasso regression. Okay. Again, importing the data, that is something that we already have. So conducting ridge regression is a little bit different from conducting regular linear regression. So the function within the package is such that it requires you to create a subset with your independent variables. So we are now going to create a matrix. Let's call it X1, like I don't know, a matrix with our data. So X1 is going to be our matrix. We are using function as.matrix. We are creating a matrix, which is in fact a data frame, and we are taking the two independent variables. So WEF as the name of our data set, $, indicating we are using the data from our WEF dataset, and then the name of our variable. So this is a little bit different from the regular linear regression. So now we have to make a subset with just our independent variables, because the function is just programmed in such a way. Okay, so we have our data, we have our subset with our independent variables, and we are now creating our ridge regression model. So we're going to call this model Ridge1 as our first initial ridge regression model. So as we said when we were talking about ridge regression, that we need to know the value of our parameter lambda. So at the beginning of our analysis, we actually still don't know what will the value of our lambda be. So that is the reason why we will need to create a couple of ridge regression models until we find the, let's say, the final one. So that is the particular reason why we're calling this model Ridge1, like the first model which we are creating. Okay, the function we will be using is glmnet. So that is the name of our function. The parameters are such that the first parameter is the matrix with our independent variables. So X1 is the matrix we previously made. The next parameter is our dependent variable. We need to indicate which family of functions are we using. We are using Gaussian family of distributions, and our parameter alpha here is 0. If we run this, if we create our model, if we go and try to print the results of our model and see the summary of our model, R is going to print us loads of lines, parameters, values, which are in fact not that useful for us. So using this, let's say, regular summary and print functions is not something that I would recommend when you are using ridge regression. So what are now we going to do? We can now play a little bit with our model, and we can see what are the values of our estimates for a particular value of lambda. So let's try function coef to see our coefficients. Our parameters of our function are ridge1, so we are using the model we previously made, and value s here is in fact our particular lambda. So now we want to see what will be the values of our coefficients if our lambda is 0.01. So R provides us with a table and provides us just with our coefficients. So this is just a test. We could have put, instead of this 0.01, any value which is interesting for us. It could have been 0.1 or 0.2 or whichever value which we wanted. This is just for us to see how this aspect works. But if we ask our question, is this the best lambda? No, we still do not know what is the best lambda for our model. So with function coef, we can see the values of our estimates based on different values of the parameter lambda. Okay. This is a pretty nice graph, which I would, recommend if you are creating or plotting ridge regression. So I think I'm not going to go and explain every aspect of the plot, but in fact we want to plot our ridge regression, for which our x variable is our parameter lambda. So we want to create a graph which is going to tell us and show us how our estimates change and drop values as lambda changes. So the whole part here related to legend is just to have, a nice graph. So if you copy paste or redo the graph the same as it is here on the slide, you will end up with a graph which looks like this. So we can see that as our value of our lambda increases, the values of our indicators, the values of our estimates are decreasing. We can see that the value of indicator goods market efficiency score is always above the value of indicator market size score. At the same time, we can see, for example, that this indicator goods market efficiency score is drops value pretty quickly if lambda increases. So this can be, a nice adding to your analysis if you are conducting ridge regression. Okay, so as we do not know what is the best value of our lambda, we will use cross-validation. So cross-validation is going to help us find the best value of our lambda. So how does cross-validation work? So we have all our data. All our data is going to be divided in training data and test data. So we are going to divide our, let's say, if we are conducting a 5-fold cross-validation, we are going to divide our data set in five sections, and we're going to make analysis, and we're going to estimate our parameters in folds. So if we divide our data to five folds, in one run one part is going to be test data, the other 4 are going to be training data. So each fold is going to be end training data and test data. So based on our cross-validation, we will try to find our best lambda. So my suggestion is whenever you are conducting analysis with cross-validation, some sampling, bootstrapping, and so on, if you want to be able to reproduce your data, it's best to set seed. So you want to set the seed of your random generator. So for example, here we used set seed to 1, 2, 3. So anytime if you want to reproduce the same, the same results, the same folds, and so on, you need to use the same seed. So here we are going to do cross validation. I think that this function by default conducts 5 or 7-fold cross validation, so we don't need to decide on that aspect. The function we will be using is cv.glmnet. So we are doing a cross validation on our ridge regression model. The first parameter is our subset, our, let's say, matrix with our independent variables. The next one is our dependent variable. We are telling which family of functions we are using, Gaussian. Now we have to tell which measure are we going to use in order to assess and find our best lambda. If you remember, we had at the beginning when we were talking about theoretical aspects, we have a graph with biasness, variance, and mean square error. So the type measure we will be using is here MSE. Alpha equals 0 indicates that we are using ridge regression. After conducting our cross validation, we want to print out our results. So print cross validation of our ridge model 1. Okay. So okay, here he did tenfold cross validation. He provides us with the results. So from this table, we can read out what is our best lambda. So in the first row, we find that our lambda, for which the mean squared error is minimum, is 0.066. So now we know what is our best lambda. So for that lambda, the bias and the variance are, in a bliss point, and our mean squared error is the minimum. So now we know what our lambda is, and now we can make our final ridge regression model. Okay, this graph it's informative but not mandatory when you are conducting ridge regression. So this is a plot which shows how mean squared error changed as lambda changed. I mean, it's not that mandatory for you to present it if you are conducting ridge regression. Okay, so for now, we would need to we can always copy the value of our best lambda, but sometimes I think it's better to be precise. So we are going to save our best lambda as an object. So best lambda 1 is going to be our saved value of our best lambda. The function we will be using, we're just reading out a value from our output. So it will be cv.ridge1. So from our cross-validation results, we want to read out lambda minimum. So best lambda 1 is 0.066394948. So now we know and we have our best lambda for this model. Okay. And finally, we are conducting our ridge regression model. Here we're going to call it ridge 1 best, like the best one we have. We are again using GLMNet. We have our matrix with our independent variables. We have our dependent variable. Family is Gaussian, alpha equals 0 indicates we are using ridge regression, and we have now an additional parameter because we know what the value of best lambda is. After that, we can list out the values of our ridge regression estimates, and they are shown in the lower part of the slide. Okay, so it is here nice to maybe present the results of ridge regression model and the results of our linear regression model. So, for example, our intercept, our constant, has increased. The value of market size score has decreased, so has increased, right? No, I'm going on the wrong way. So the value of estimate regarding to market size score within our ridge regression has reduced. The same accounts for the estimate of good market efficiency score coefficient. So from 0.60, now it is 0.568. From 0.134, now it is 0.131. So we can see that the values of our estimates have shrinked a little bit compared to our original linear regression model. Okay, so with this we finished doing our ridge regression model. Do you maybe have some questions or comments on this part of the analysis? Okay, then we can slowly continue to lasso regression. So many things that we have introduced for ridge regression are going to be almost the same when doing lasso regression. So what we said is that lasso regression is related to adding a constraint which takes into account the sum of absolute values of our coefficients. So more or less, that is the main difference. The thing, again, which we will have to deal with is the question related to lambda. Again, we don't know what the true value of lambda is. If lambda is 0, our lasso regression is the same as linear regression. If our lambda tends to infinity, all our regression coefficients are going to be 0. So lasso regression compared to ridge regression is tending to reduce the values of your estimates even more. So within lasso regression, it is easier for an estimate to take a value of 0 than it is within ridge regression. So again, our procedure for finding the good value of lambda is going to be through cross validation. So again, we have graphical representation. Point B is the point with OLS estimates. We want to reduce the values of our estimates, but here, as we can see, where the point where the red line and the blue surface are touching each other is in fact the point where value of one estimate is going to be 0. So in this point here, the value of estimate B2 is going to be 0, while the estimate of B1 is going to be here. So as we can see, when we are using lasso regression, we can more easily reduce the value of one indicator to 0 as presented here. So again, this is the graphical interpretation. Again, we are shrinking the values of our indicators, and we can see that more easily they're reaching the value of 0. So in fact, if you are interested in maybe reducing the size of the complexity of your model, so lasso regression is maybe a better option, because it can easily, with more ease, reduce the values of your estimates to 0. Okay. So also, we can now even compare ridge and lasso regression. So lasso regression creates a subsample of your independent variables. As we saw, lasso regression more easily shrinks the values of your indicators. The prediction accuracy of both of these two regressions are almost the same. So definitely there is no perfect answer whether ridge regression is better or lasso regression is better. So then the question arises, why not make a combination? Why not take both of them in account and take both types of constraints into account when estimating your values of coefficients. So in fact, therefore, a new type of regression was created. So a combination of both lasso and ridge regression is regression called elastic net. So if we observe the function for the elastic net, which needs to be solved, this part here is related to ordinary least squares. This part here is related to constraints from the ridge regression. This part here is related to constraints from lasso regression. So here we have to have in mind that if alpha is 1, our model turns to lasso regression. If alpha equals 0, the model turns to ridge regression. So within our function in the GLM net function, if we remember, we had parameter alpha. So if alpha is 0, we are creating a ridge regression. If alpha is 1, we are doing a lasso regression. So we can also play with this value as well, and we can have a combination of both lasso and ridge regressions. Okay, So we are going to redo our analysis. So again, we are creating the same model as we created for ridge regression, but now we are just creating a lasso model. So basically, the function GLM-net is going to be the same. The thing which differs is the value of alpha. As we said, if alpha equals 1, we are creating a lasso regression. So the procedure is going to be the same as we had it for ridge regression. So first we create our basic lasso regression model. As we saw, functions summary and print are not that useful for us. We can play a little bit, as we saw. We can try different values of our lambda. Here we took lambda to be 0.01. It could have been 0.05 or whichever value we are interested in. So even if we look now at these coefficients, we can see that they are reduced from our OLS basic coefficients. This one here was 0.6 something, and this one was 0.13. So definitely our estimates are going to be reduced. Again, we don't know the best lambda. We are again going to turn to cross validation. Also, we can create a pretty nice plot to see how our estimates are going to change as lambda changes. A similar one that we saw in ridge regression, but we can see that now the shape of our estimates and how they are changing based on the value of lambda is pretty different. So we can see that the good market efficiency score, for example, it took quite some time before it started to sharply decrease. For example, that could be one, let's say, small interpretation. But as I said, these graphs are are a nice addition to your analysis. Again, we're doing the cross validation. Again, my recommendation is to set seed. All parameters within the function are the same except alpha. So alpha is in fact the parameter telling you whether you're using ridge regression or lasso regression. So we're going to print our results, and here we, for example, see that the best value of our lambda is 0.002. 228 if we want to be precise. So definitely it's good to use cross validation because you don't know what the value of our lambda is. So to be sure that you're using a good value of lambda, it's best to use cross validation. Okay, again, the informative graph, how mean squared error changes as lambda change. I mean, it's not that mandatory to present in your paper. Again, we need to save our best lambda and use it in our final lasso model. Okay, so again, we're using GLM-net for our final model. We have our matrix with our independent variables. We have our dependent one. Family is Gaussian. Alpha 1, we are doing the lasso regression, and we are using the best lambda we found. And this is our final model. So I think it's pretty good to present all of our all of our analysis in one on one slide. So as we can see, values of our indicators have been reduced. In some models a little bit more, in other models a little bit less. But please have in mind that here we had a pretty simple multiple linear regression model. Imagine if we had, for example, 10 or 15 independent variables in the model. Using these approaches to regression could have helped us to reduce the number of variables in the model. So yeah, this would be the part. If we are interested in using the elastic net model in R, we would be needing an additional package, the package Caret. So we would need to install the package and activate it if we want to create an elastic net model. We said that an elastic net model is in fact a combination between Lasso and Ridge regression. So it will take into account both types of constraints in the model. Okay. So here, let's say we will want to do cross validation, and we want to use a cross validation with five folds. Here the function is maybe a little bit more complex. We want to create the training model using the function train. After obtaining the results, this would be our GLM. This would be our results. So here the function is such that it will provide us results for different values of alpha. We remember that alpha is in fact telling us how much of which constraints we will be using. So we have several solutions provided. So for different values of alpha, different values of lambda, we have obtained different mean square error and root mean squared error. So also the analysis tells us which is the best model we created. So in this case, the best elastic net model is the model for which alpha is 0.1 and lambda is 0.0759. So those are the parameters creating a model which takes into account ridge regression constraints, lasso regression constraints, and creates a good model. If we additionally want to expand the search space for a good combination of alpha and lambda, here we have tune length additional parameters set here to 10 to create more models. So here it's up to us to define what will our search space be. I mean, here the tricky part is that you don't know which value of alpha is the best. You don't know which value of lambda is the best. So definitely approaches such like this, where you are expanding your search space and trying allowing the software to try different combinations of these parameters is pretty good. So now when we have expanded the search space, we found a different combination of alpha and lambda, which maybe provides a better solution. So here our best alpha would be 0.1 and the best lambda here would be 0.0266. So this is maybe a tricky part related not just to elastic net, but also maybe to both ridge and lasso regressions. Okay, these are also some functions already fixed like this, which you can copy and use, which can help you find best combinations of alpha and lambda. So this would be the final output. But for you who are want to do ridge and lasso for the first time, it's enough to do or one or the other, because the elastic net model might be a little bit more complicated, both to conduct and later to explain to maybe decision makers the results of the analysis itself. So with this, I would finish this, let's say, shorter tutorial on the lasso and ridge regression in R. I hope you found the tutorial useful, that you learned something new about both lasso and ridge regressions and different approaches to regularization of linear regression models, and that you also saw how you can conduct these analysis in R. So for now, that would be it from my side. So if you have any questions, comments, I'm here to answer them.
Okay, thank you, Maria. Milica, it was very interesting tutorial that you gave today, and thank you everyone for watching the tutorial.